My name is Jim Al-Khalili, and I'm Emeritus Professor of Physics at the University of Surrey. My book is called On Time, the Physics That Makes the Universe Tick. If you look up the problem of time online, there'll be various definitions of what is regarded as the problem of time. I like to lay out 4 different distinct problems. One is whether time flows. The second, how can we reconcile quantum field theory with Einstein's general theory of relativity? Third, what is special about now? The fourth and final problem of time, where does this direction of time come from? At the end of this interview, hopefully we'll lay out the problems and the questions and the paradoxes, some of which we've figured out. Others remain. For me as a physicist, I try to understand the external world, try and make sense of it. And to do that objectively, we have to sort of extract ourselves from the thing that we're studying. When it comes to time, there's a problem because we are unavoidably embedded within time. We can't extract ourselves from it and view it objectively. Very often, physicists and philosophers who study the nature of time make this distinction between physical time that is embedded within the laws of physics and our own perception of time, psychological time. I like to use the term manifest time. I think it was first used by the philosopher Craig Callender. So manifest time is a way of compartmentalizing our perception of time from time that is external to us. One of the most powerful distinctions between our perception of time, manifest time, and physical time, time that appears in our laws of physics, external to our senses, is this notion that we feel very strongly that time is flowing, that there's some continuum, that there's change. We tend to think that time, and this is quite a strong feeling, we tend to think that time speeds up as we get older. Where did time go suddenly? I'm the last 10, 20 years ago, my kids have grown up. How did that happen? And yet, your childhood seemed to stretch on forever. So there's a theory that suggests it's to do with the laying down of new experiences. It's true that, 1 year when you're 5 years old, the period between one birthday and the next, is a really long time. 1 year when you're 50 years old goes by in a flash. There's the opposite property to time when you look at shorter intervals. So rather than the laying down of new experiences and being active slowing time down, compare half an hour sitting in the dentist's waiting room where you have nothing to do, and you haven't got your phone on, you're not reading anything, with half an hour at a party where you're enjoying yourself. Now, at the party, you're laying down new experiences. You're meeting people, you're chatting to them, you have a lot of input coming into your senses, and yet that half an hour at the party just goes by much more quickly than the time that drags when you're sitting in the dentist's waiting room. A concept closely related to the nature of time is the idea of change. When something changes, we think of it in a common sense way as changing over time, as time flowing and something changes. This idea goes all the way back to the ancient Greeks, who couldn't agree on whether time was fundamental, that it had to exist, and then change happens within it, or whether change is the fundamental concept and time simply reflects that something changes. Physicists have argued about this, and they argue about it to this day. So the great physicist Richard Feynman said that time is what happens when nothing else happens, that somehow time exists in and of itself. Isaac Newton had the view that time was external to the universe, external certainly to space and things that happen within space, that there's this cosmic clock that inexorably ticks by the seconds, the minutes, the hours, the years, regardless of what we are doing. We can't stop that time. We're just caught in the flow, and time keeps on going. So that absolute notion of time is something that Isaac Newton explained, and it's something that in everyday life, I guess, is the common sense view of time, that there is this external clock that's ticking by regardless of whether we think time is speeding up or slowing down. Of course, that idea of an absolute external time was thrown away entirely when Einstein developed his theories of relativity. Einstein explained there is no such thing as absolute time. Time is relative. And yet, we still have this strong psychological feeling that there's a past, there's a future, there's a now, there's a flow. We know our consciousness is moving along this river of time, gobbling up the future, spitting out the past. The present moment is ever changing. So that notion of change is embedded within this idea that time is flowing. And yet in the laws of physics, there is change, but there's no flow in and of itself to time. In most of our equations of physics that describe how something, a system, changes, yes, it changes over time, but time comes in a very almost trivial way, as a humble coordinate, a number, a parameter, a symbol, lowercase t that sits inside your equation. It's not changing. If you have an equation that describes a system, you can just look at the math, look at the equation. Well, what does it mean when we evolve this equation in time? Well, it just means we're solving this equation for a value of this coordinate. What a system is doing now is described by what it's doing at this particular value of coordinate time. But we can also evolve it forward and see what it's doing at a different value of coordinate time in the future, or evolve it backwards to see what it was doing in the past. But there's no flow, there's no real change there. Time is simply a number that appears in the equations. And there must be more to time than that. Well, certainly that's our psychological feeling about time, that there is change and we experience this change as a continuum. Where is that change? Where is that flow in the equations of physics? It doesn't exist. So it seems quite natural to us that time can speed up or slow down depending on what we're doing. If you're having fun, time goes by quickly. If you're bored, time drags. But we know that's just in our subjective experience. It's not what really happens to time. Surely, external to our experience, time continues at a constant rate everywhere in the universe. Well, of course, that's Newtonian time, and that's the time of our everyday experience. But Einstein comes along and says, actually, the idea that time speeds up, slows down, isn't just subjective, isn't just in our heads. There is a real physical phenomenon whereby time can run at different rates for different observers, what we say in different frames of reference. That was a revolution in physics. Einstein, of course, had two theories of relativity. The first one in 1905 was forced upon him by not studying the nature of time and space initially, but by studying the nature of light and the speed of light. Physicists in the late 19th century had been searching for the medium that carries light. Now, light was known to be a wave. Light, therefore, physicists believed, needed something to travel through, some medium, this ether. The fact that they couldn't find it was very puzzling, and Einstein overthrew the whole concept of what time and space means by suggesting that light doesn't need an ether at all, which means that however fast you're moving relative to someone else, you should still see light moving at the same speed. What does this mean? If I shine a torch out into space, and then a friend jumps in a rocket and flies, let's say, at 3/4 of the light speed, so I will see light overtaking them in their spacecraft at 1/4 light speed. Einstein says you would expect that they would see light overtaking them at that same speed. But no, they would still see that light overtaking them at the same speed that you see it leaving you. All observers, however fast they're moving relative to each other, will see light moving at the same speed. It shouldn't make any sense at all until you realize that they must have different concepts of space and time. And in fact, my friend traveling in the spacecraft trying to catch up with this light beam, if you were to look at their clock on board their spacecraft, you'd see it ticking by more slowly. That's the sums work out. You change the nature of space and time in order to preserve the constancy of the speed of light for everyone. So Einstein came to this conclusion in his special theory of relativity due to the constancy of the speed of light and the fact that all motion is relative. So no one can say, I am definitely standing still and you're moving, to come up with the idea that time and space get altered. And since we're talking here about the nature of time, this is what leads to the idea of time dilation, that time can be seen to run slower on a moving clock as it moves past you. Now, if someone's moving past me close to the speed of light, I will see them doing everything in slow motion. It's just not just that their clock is moving slower, somehow their high speed is messing with the mechanics of the clock. That whole frame of reference, I will see time running slower in it. However, since all motion is relative, the person on board the spacecraft that I see behaving in slow motion would see me behaving in slow motion, because for them, I'm doing all the moving. And so it's my time that is running slower. This idea of time dilation seems like just a thought experiment or some notion that Einstein's come up with. Surely it doesn't happen in the real world. Well, it does. For example, muons are subatomic particles that are created in the upper atmosphere. Cosmic rays hit the molecules of air in the upper atmosphere, and the energy from the collision creates a whole stream of particles. Among them is this particle called the muon, which is like the more massive cousin of the electron. Muons aren't like electrons in the sense that they're not stable. They only live for a fraction of a second. These muons that are created in the upper atmosphere then stream down to Earth. Now, we can measure how fast they're moving, close to the speed of light. Nevertheless, for the distance they have to cover at that speed, they would have to live a lot longer than their normal lifetime, the lifetime they would have at rest. But of course, they do manage to get down to the ground, and we can capture muons in our detectors, so we know they've arrived from the upper atmosphere. How do they do this? Well, because they're going close to the speed of light, their clocks, their internal clocks that tick by their lifetime, slow down. So they are living their life in slow motion, which gives them enough time to reach the Earth. Now, the counter explanation to this is, how does the muon see things? Surely, if all motion is relative, the muon sees our clocks running slower. Well, of course, from the muon's perspective, something else happens when you go close to the speed of light, namely distances shrink. So along with what's called time dilation, the slowing down of time, there's length contraction. And the length contraction is the distance the muon has to travel from the upper atmosphere to sea level. The muon is moving so close to the speed of light that it sees this distance shrunk. And it says, well, I'm only living for 2 microseconds. I'm counting how long I'm living for. The reason I can get down to the ground is because I don't have to travel that far. So everything fits and works logically. But this idea that time slows down is real. This notion of time dilation is part of Einstein's special theory of relativity. There's another way that time slows down, and that is part of his general theory of relativity, which he developed a decade later. And that's where we have to bring gravity into the story. You see, in special relativity, it's all about things moving at constant velocities, no acceleration, no speeding up, slowing down, going around in circles. Things have to move in a straight line at a constant speed. And then you can use the rules of special relativity to talk about time intervals and lengths and how fast clocks tick and so on. Once Einstein wanted to generalize that, he realized he had to bring in acceleration. What he referred to as the happiest thought of his life was something we now teach as the principle of equivalence, which is to say that acceleration is equivalent to gravity. Now, we're sort of aware of this in everyday language because when a car or an aircraft is accelerating, we talk about the G-force. Now, that G is G for gravity. So when you're pushed back in your seat as your car accelerates, that's exactly the same force as you feel when you're laying down with your head resting on the pillow, if you're accelerating at 1G. This principle of equivalence led to the idea that in order to explain the structure, nature of four-dimensional space-time, one has to come up with a different picture of gravity, since gravity is linked to acceleration. And that led to Einstein's general theory of relativity, which was a theory of gravity that replaced, yet again, he's replacing something that Newton has given us. In general relativity, Einstein gives us a new picture of gravity. In that intervening 10-year period between special theory in 1905 and general relativity in 1915, Einstein and other physicists realized that time is the fourth dimension, and it's actually, you have to talk about it in terms of four-dimensional space-time. His general theory says, yes, time is the fourth dimension, it's part of space-time, but gravity curves space-time. Gravity changes the shape of space-time. Now, we can't perceive space-time as a four-dimensional whole. We can only have instruments that measure distances in space or clocks that measure intervals in time. So we have to sort of separate the two. So how does that look to us? Well, time gets slowed down by gravity. And again, this is not an optical illusion. This is, in a sense, more fascinating, more fun than the time dilation of special relativity, because special relativity requires, you only see that effect when you're going close to the speed of light. When I explain this, for example, when I give schools talks, and the kids will ask, how do you know? You're just making this up. So, well, every one of you that uses a smartphone, you use GPS, you use Google Maps, you are making use of the fact that time is running at different rates depending on how strong gravity is. You see, the closer you are to the surface of the Earth, the stronger the gravitational field and the slower time runs. The further out you go into space, the weaker gravity is and the faster time can run. It's only just tiny fractions of a second, but it matters. GPS, the satellites that are sending radio signals down to our phones, they are in orbit around the Earth. They're feeling slightly weaker gravity than the clocks on Earth. And so time is running faster on board those satellites than it is on Earth. So we have to take this into account, in a sense, slow down the clocks on board the satellites so they synchronize with clocks on Earth. Because if we don't do that, satellites would not be able to locate our position accurately. So it's a real effect. It's true, that my head is aging faster than my feet by tiny, tiny fractions of a second, but it's there. And of course, it gets much more dramatic if you go and find a much stronger gravitational field. It sounds ridiculous, but actually, the physics is all correct. We're used to describing events that are happening at a point in space and a moment in time. So in physics, when you want to define an event, say the snapping of my fingers, it happened at this point in space and at that moment in time, we need 4 numbers to describe it. We know that. Even Isaac Newton would have understood that. In special relativity, once we unify time and space, time is not just another disconnected number, a place in space and a moment in time. It's a point in 4-dimensional space-time. Time is this fourth dimension. Now, Saying time is the fourth dimension is easy enough, but what does it actually mean? We can't visualize 4 dimensions. We can only visualize 3 dimensions. Our brains are 3-dimensional. There's a trick we can do here. So I have a 3-dimensional construct. What if time replaced the 3rd spatial dimension? Now I have a 3-dimensional construct, 2 of space and 1 of time, that I can visualize. And this leads to an idea very useful in physics called the block universe. In a sense, it's a bit like sheets of paper in a book. So each sheet or slice is all of space at one moment in time. At the one end is time at the earliest moment. The direction is the time axis. And then you have these slices of space for each moment in time. Now, we experience time as going by continuously, but you can imagine there's a slice for every moment in time. So the idea of a block universe is very useful because we can now draw a picture of it and think about space-time having thrown away one of the dimensions of space. What does it then mean for us to be moving through space-time? Well, here, physicists use the idea of a world line. So this is a line that moves through this block universe. It can start at a particular point, which coincides to a point in space and a moment in time, and ends with another point in space at a later moment in time. Every one of us has a world line. My world line began when I was born. I mean, let's make an approximate point about that being the moment of my birth, being the beginning of my world line, and it will end when I die. That world line isn't a straight line, it's wavy, because although I'm moving through time, I'm also moving through space. Now, if I were to spend my whole life without moving, then I would have a straight line, world line, but actually it waves as I move through space while traveling through time. And physicists use world lines very usefully when it comes to describing things like particles colliding with each other and how they move and the speed that they're moving at. Probably the most ambitious project in physics over the past, certainly half a century or more, has been to reconcile quantum mechanics, or more correctly, one should say quantum field theory, which is the more modern reincarnation of the quantum mechanics of 100 years ago, quantum field theory with Einstein's general theory of relativity, namely the theory of the very small that has time as a coordinate, and the theory that describes the structure of space-time itself. One early attempt at doing this led to what we call the Wheeler-DeWitt equation. John Wheeler and DeWitt, Bruce DeWitt, were two cosmologists who tried to come up with a way of unifying quantum mechanics and relativity theory, and devised this equation, which has a very remarkable and strange feature, namely that it has no time in it. It just is. And this is an equation that one can argue describes the state of the entire universe, the quantum state of the universe. And there's no time in it. So this would then add support to the notion that at a fundamental level, time is an illusion. Time doesn't really exist at all. Now, of course, the Wheeler-DeWitt equation describes the universe as a whole, and you can only really appreciate the universe as a whole if you are able to extract yourself from outside it. We only ever view the universe from within. But the Wheeler-DeWitt equation has led to the idea that since we perceive time, seems very real in other areas of physics, maybe time is a so-called emergent property of reality. Now, emergence is a rather complex notion. There's what you might call weak emergence, which is the idea that, for example, an example of weak emergence is the wetness of water. Right? You can never you can't appreciate the wetness of water just by examining one H2O molecule. You need trillions and trillions of water molecules to come together, and the notion of wetness appears. Or temperature is another example. There is no such thing as temperature when you're just looking at one or two molecules bouncing around and bumping into each other. But zoom out and look at a box of gas molecules bumping into each other, and suddenly you get this notion of temperature that you can ascribe to it. We could, if we studied the microscopic structure of a system enough, deduce that once you scale it up, you will see properties like temperature or the wetness of water emerging. Then there's the notion of strong emergence, which is, so consciousness is a good example of that. That you could never hit upon the idea of consciousness just by looking at the interaction of individual neurons in the brain. So emergence is something that grows out of something more fundamental. And there's been this argument that time is also an emergent property. It grows out of something deeper, something more fundamental. And the suggestion is that deeper thing is embedded within the quantum realm. So in quantum, even though in quantum mechanics and the famous equation of quantum mechanics, Schrödinger's equation, Erwin Schrödinger developed his equation 100 years ago, and it describes how the quantum state of an atom evolves in time. That's an equation that does have time in it. We teach physicists at university that this Schrödinger equation that depends on time can be tweaked and modified, and you can arrive at a new version of it, which is called the time-independent Schrödinger equation, where time doesn't exist at all. The Wheeler-DeWitt equation for describing the whole universe, which brings gravity into quantum mechanics, behaves in a similar way. You've extracted time from it entirely. So how is it then that time emerges from a timeless universe? And that is still a subject that's being studied and debated and argued about today. In order to then try and have some concrete idea of what time is, philosophers have come up with different ways of describing, whether there was a special present moment that divides the past from the future. Einstein tells us that time is the fourth dimension. And others will argue that time doesn't exist at all. It's all just an illusion. It's a construct. It's something that we've invented, or it's the thing that clocks measure. So, for example, if we divide time up into its three parts, the past, the present, and the future, one might argue that the past has gone. We no longer have access to it. All we have access to is records of the past, but these are records that we'd only access in the present moment. The actual events of the past are gone. They don't exist. The future has yet to be, even in a deterministic universe where everything is preordained. Nevertheless, the future hasn't happened yet, so it doesn't exist. All that leaves is the present moment. But the present moment isn't extended. It's the dividing line between the past and the future. It's the shadow between the light and the dark. It doesn't have an existence in and of itself. It's just the gap between them. So if the past doesn't exist, the future doesn't exist, and the present doesn't have any extent, it doesn't exist either, we've done away with all of time, then time is an illusion. Now that sounds a bit like sort of a philosophical trickery, and in a sense it is, because there's the opposite view, which is the one that's given to us by Einstein, which is to say that if time is the fourth dimension, then just like the dimensions of space, all points in space exist and are equally real. If time is also a dimension, then all points in time exist and are equally real. Therefore, rather than the past, present, and future all being an illusion, they are all equally real. They all exist. Time is, in a sense, frozen. We experience a present moment. We are sort of, you can think of it in terms of our consciousness drifting along that time axis, and we're stuck on that rail. We're moving along. But the time itself, for all eternity, just is. All times coexist. So this is an idea called eternalism. And I think probably, if push comes to shove, most physicists would subscribe to it, because we know that Einstein's description of time is the best one we have. The idea of eternalism, that all times are equally real in the block universe, can seem quite bleak. Now, we already had a notion that reality is rather bleak if we follow what Newton taught us, namely that we might well live in what's called a deterministic universe, where the future is predetermined, preordained, even though it hasn't happened yet. That's what's called the clockwork universe, where everything's ticking by mechanistically and everything. Causes lead to effects. And, if we were powerful enough, we could work out what those effects will be. We could predict the future. In reality, we can't predict the future for a number of reasons. But in Newton's clockwork universe, even though that future is preordained, it's destined to be, it still doesn't exist. And so we can still imagine that we have free will, free agency. Maybe you look back after something has happened, you say, well, it was ever thus, that was ever going to be the way it has, because the universe has evolved deterministically. But when it comes to the block universe and eternalism, that future, it's not that future has yet to unfold, it's already there waiting for us. Somehow that is a more stark description of determinism and a stronger assault on free will. What's the point of me thinking that I'm making free choices if that future is already out there? Now, of course, what saves us is that we are embedded within the universe, within the block universe. If you could pull yourself outside of space-time, the so-called God's eye view, you could see all times mapped out. You could see exactly past, present, and future all equally real. But we don't have that privileged vantage point. We are embedded within the universe, and even in a fully deterministic universe, the fact is we can never predict what is going to happen in advance. We are unable to predict it. So you may refer to that as just the illusion of free will, but for me, I think that's good enough. So I subscribe to a philosophical view called compatibilism, which says that, yes, I have free will, even though I live in a deterministic universe. And the reason I say that is because even if the future is preordained and set out in the block universe, in this eternalist picture, I'm never able to predict it in advance. So I'm thinking of making free choices, and that's good enough. Of course, eternalism, the idea that all times, past, present, and future, all coexist, according to relativity, isn't the only option available. Philosophers have also argued that maybe an alternative idea is what's called presentism, which is that only the present moment exists, or past presentism, the past and the present exist, or the growing universe model where the past and present exist but slowly gobble up the future. There's something called the spotlight theory, the idea that it's a light shining on one moment that's changing along the time axis. But the problem with all these alternative theories to eternalism, presentism, past presentism, and so on, is that they come into conflict with all our current attempts at coming up with a theory of quantum gravity. Whether one subscribes to things like string theory or loop quantum gravity, all these mathematical ideas that unify quantum mechanics and relativity all seem to require the eternalist picture. It's the one that makes most sense when we're trying to combine quantum mechanics and relativity to solve this this problem, the first problem of physical time. And of course, most importantly here is that the eternalist picture says there is nothing special about the present moment. There's nothing special about now. We experience now subjectively and think it's special, dividing the past from the future. But in physics, there's nothing special about this moment. It's just a point on the time axis in four-dimensional space-time. Even in Einstein's special theory of relativity, we can appreciate that the concept of a now, an absolute universal present moment, simply doesn't make sense. One can imagine two events I can experience two events that to me seem to have happened at the same time. They're simultaneous events. Now, if I know they took place at an equal distance from me, then even though it's taken some fraction of a second for the light from those two events, the signal to reach my eyes, I can work backward and say, well, if I saw them happening at the same time, going back, they must have actually, like flashes of light. Those flashes of light will have happened simultaneously because I'm halfway between them and I saw them happen at the same time. But for another observer moving past me at close to light speed, they will not look as though they've happened at the same time. And this is something that generations of physics students have to learn, something called the relativity of simultaneity, which very clearly shows that what one observer regards as now, as two events happening at some moment in time that they say is happened now, another observer will disagree, say, no, one event happened before the other. In fact, we can even imagine a scenario where I see one event happening, let's call it event A, happening just before event B. For another observer moving very fast relative to me, they may see event B happening before event A. So where is now if our past and future are mixed up? Now, of course, we can't, what we're forbidden from doing is something called the violation of causality. So if event A was the cause of event B, then no one can see B happening before A. You know, if event A is me shooting a gun and event B is someone being shot and falling down, you're not going to see them being shot before I fired the gun, because you can imagine them then stopping me from firing the gun even though they've already been shot. I know that's a rather violent example. I don't tend to use violent examples in physics, but there we go. That might illustrate it. But the fact is, if one event can affect the other, then there is an order that you can't mess with. Cause has to come before effect. But if those two events are far enough apart and close enough in time such that there's not enough time for a light signal to transfer between them, then we say they are not causally connected. And in physics, we talk about them as being space-like separated. So in that case, events A and B can have their order fuzzy. Someone can see A before B, someone else can see B before A. And once you realize this, you realize you cannot pinpoint a universal present moment if we can switch past and future around. So that present moment becomes rather fuzzy, according to relativity theory. And while in relativity theory, we clearly see there's a fuzziness about what we would refer to as a universal now. No such thing exists in relativity. Even in manifest time, our psychological or experience time, there's a fuzziness about what it means to say now. Apart from the fact that it's ever changing. You pinpoint a moment in time as now, but it's already in the past by the time you've said it. But the notion that now is a moment is also really not something that we see in psychological time. It's an extended presence. It has a thickness to it. To begin with, when an event happens, of course, in relativity, I said events A and B happen, and there's a certain finite time for the light to reach my eyes from the events. There's a further time for that light to enter my eyes, travel to my brain, be processed, and for me to be conscious that event has taken place. So there's what's called perceptual latency, a delay between an event happening and us being conscious of it. And that can be anything from, up to like a third or more of a second later. So when is it that we should regard something as happening? When it's happened or when we're conscious of it? There's already that fuzziness there. But let's say that's the moment that something happens. What about when does and the now start for us? Well, again, it's rather fuzzy. An example is how we appreciate a piece of music. We don't just hear one note at a time that replaces the previous note because that's gone and it's in our past. No, we experience music as a continuum. And the way we do this is through what's called episodic memories. We are storing memories of events in our brain that are then stitched together in a continuum so that it's not just the present moment note that we are conscious of. We're conscious of some finite time in the past weaved together to give us the music that we appreciate. Added to that, the fact that we anticipate where the music is going in the future, even though we haven't heard it yet. And so what we'd regard as the present now is really an extended period of time that relies on past events that are still stored in our memory that we have access to, even though we are only ever accessing any moment in the past in the present moment. It's still there, and it gives us this sense that we're experiencing a flow of time or a finite duration of a present moment. Well, if there's nothing special about now, about the present moment, we still have to admit that it divides up the future from the past. So what is it that's different between the past and the future? Certainly, it sounds almost tautological to say the past comes before the future. That's what the word before means. But there's this asymmetry. They are different, certainly in the way we perceive them. And the flow, even though we might decide that the flow of time is an illusion, there's certainly a directionality to time, pointing from the past to the future. Many physicists will argue this is due to the arrow of time, that the difference between the past and the future is due to what's called the arrow of time. But you don't need an arrow to talk about what's different between them any more than you need an arrow to point from the shallow end of a swimming pool to the deep end to tell you there's a difference between the shallow end and the deep end. They are just different. Nevertheless, we experience time moving only in one direction, that time is irreversible. Now, is that irreversibility just something, again, that we can regard as an illusion in an eternalist picture? Or is there really an arrow of time? Well, the third area of physics that gives us a direction to time really stems from 19th century work of people like Ludwig Boltzmann and the laws of thermodynamics. One of the most famous ideas in physics is the second law of thermodynamics, which is always amusing that it doesn't even make it to the top of the list of laws of thermodynamics. It's only number 2. And yet it is regarded as almost sacred in how true it must be. Even Einstein said if you can't reconcile time as a coordinate in quantum mechanics and time as a dimension in relativity theory and time as a direction or arrow in thermodynamics, then it's the arrow of thermodynamics that's the one that's going to survive. The other two may have to go if we want to come up with some theory that unifies all these concepts. So where does this arrow of time come from? Is it real or not? Now, the reason why physicists hesitate with this is that nowhere else, other than in thermodynamics, is there this notion that time has a directionality. All our fundamental equations of physics are time symmetric. We say they're time reversal invariant. If you change the sign of the symbol time, the coordinate time in the equations, if you make t minus t, and more often than not you have to make a few other tweaks as well, which we don't need to go into, then you realize that the system that this equation describes evolves perfectly well in the opposite direction. So time can move forwards or backwards, and these equations would describe physical reality very sensibly. Time is symmetric according to the laws of physics, and yet we see irreversibility all around us. I get older, balls roll down hills, batteries run out of charge, things decay, get older, the universe gets bigger. Wherever you look, you see things happening in one direction of time, but not in another. And this is the fourth problem of time, the second problem of physical time, namely, where does the directionality of time come from if all our fundamental equations of physics are symmetric in time? Normally, when we talk about the arrow of time, the direction of time pointing from past to future, we have to explain the concept of entropy. Now, entropy it's not a vague concept, it's just a very versatile concept because it can mean very many different things. The simplest way of describing entropy is to say that it's what follows from thermodynamics and statistical mechanics, that things move from higher ordered states to less ordered states. Disorder increases. A box of gas where all the molecules of the gas are all squashed together in one corner of the box, we say that has high order. It's neat and tidy, and it's a very special state. But as the molecules diffuse and fill up the box evenly, entropy increases. So there are many ways of describing entropy, but basically we say entropy always either stays the same or increases in an isolated system. This is what the second law of thermodynamics tells us. But what happens when entropy has reached a maximum? In a box of gas, what happens when all those molecules of gas have spread out evenly? Now, if you were to zoom in and look at the detailed motion of the molecules, you'll see them all jiggling about. But if you were to film them jiggling about and then run the film backwards, you wouldn't be able to tell the difference. Because at what's called thermal equilibrium, things look exactly the same forwards and backwards in time. I've had this argument with other physicists who will say the arrow of time disappears at thermal equilibrium. Well, sure, it disappears in the sense that we cannot perceive a direction to time. We can't tell the difference between a movie running forwards and backwards. But that doesn't mean that time has ceased to go on. Of course, if you could extract yourself from outside of this box, then you will see entropy continue to exist outside. But what if the whole universe reaches thermal equilibrium in some distant future, the heat death of the universe, where everything is dispersed, all matter has fallen to black holes, and black holes have evaporated out, and everything is just thermal radiation, all sort of moving apart as the universe expands. At thermal equilibrium, does time cease to exist? Well, I would argue no. Just because you can't perceive a direction to time doesn't mean that it's not going by. Indeed, if the universe continues to expand forever, as our current theories would suggest, then time is pointing in the direction of expansion of space, the cosmological arrow, so-called, of time. And in any case, we would never be able to check whether there's time going on or not, because at thermal equilibrium, we can't exist. We are special states. That's what defines life. We are low entropy constructs that have some complexity. At thermal equilibrium, we have to be part of this thermal even spread of everything in the universe. Now, of course, what's interesting is that even at thermal equilibrium, maybe entropy can fluctuate, maybe, just randomly, in the same way that you can shuffle a pack of cards, and when it's fully shuffled, you really can't tell whether it's any more shuffled or less shuffled. But maybe now and again, just through chance, very unlikely, but just through chance, you may shuffle it and retrieve some order. You'll get a sort of a running flush, as a poker player would say. Suddenly you get cards that are ordered just through sheer chance. What happens in a universe at thermal equilibrium, where just through sheer chance, you suddenly get temporary, isolated bits of the universe that have lower entropy, that have moved away from equilibrium. This is something called Boltzmann brains. The idea that there is a non-zero, albeit, highly unlikely, a non-zero chance that's out of thermal equilibrium at maximum entropy, some lower entropy state can appear temporarily and then disappear again. So things can still happen at thermal equilibrium, but certainly time, just because we can't perceive which direction it's going, doesn't mean it isn't continuing to evolve. One area I've been interested in recent years is what's called open systems, or more specifically, open quantum systems. So the idea that the dynamical equations of physics that we know and love really almost all apply to what are called isolated systems, systems that are isolated from their surroundings. But we know that nothing is completely isolated from its surroundings. There's this wonderful example of molecules of gas in a box that are bouncing around, and the way they evolve in time after multiple collisions depends on so many factors. Has origins things like the butterfly effect, how the flapping of the wings of a butterfly on one side of the world would eventually lead to a storm on the other side of the world. Small initial conditions can grow. Well, the presence or not of a single electron on the other side of the visible universe will affect how these molecules, its gravitational effect, will change the dynamics of these molecules after about the 50th collision. This is the calculation that has been done. Nothing can be entirely isolated from its surroundings. What this means when it comes to reconciling the arrow of time with time-symmetric equations is that it's the time-symmetric equations that have to give way. Now, normally, physicists look at it the other way around. They say, look, how does a directionality to time emerge from time-symmetric laws of physics? Well, I'll put it the other way. Time-symmetric laws of physics are idealizations that only apply to truly isolated systems. There is only one truly isolated system, and that's the entire universe. Everything within the universe ultimately, eventually interacts somehow with its surroundings. And that interaction with its surroundings kills any notion of time symmetry. It brings in a directionality to time. And down at the quantum level, this really has a profound consequence, because a quantum system not only is disturbed by its surroundings, but it becomes entangled with its surroundings. And that is a truly irreversible process. Well, rather, when it becomes sufficiently entangled with its surroundings that it leads to what's called decoherence, the quantumness it dissipates into the environment, you cannot retrieve it. So decoherence is regarded as the one truly irreversible process in nature. But since it's prevalent everywhere in the universe, decoherence is always taking place, that brings in a directionality to time that is fundamental. So when people argue or ask, where does an arrow of time come from when you have time-symmetric equations? Well, the arrow of time is already there. I would argue that the arrow of time is baked into reality. It's baked into the universe, fundamentally due to quantum entanglement and quantum decoherence, increasing all the time. So just as entropy increases, we can describe entanglement increasing. We can even define something we've tried to do in recent years, define the entanglement entropy, not the thermodynamic entropy of increasing disorder, the melting of ice cubes in a glass of water, the shuffling of the cards, the dissipation of air molecules in a box, the spreading of air molecules. That's all thermodynamic entropy. There's also what we might regard as entanglement entropy. Increasing entanglement of a system with its surroundings is inevitable, and it gives us a direction to time. And the time-symmetric equations that we know and love are simply idealizations in the limit when we can ignore the surroundings of the system we're interested in. So if I believe that the direction, the arrow of time, is baked into reality, well, you can't have a direction of time without time itself. It's the smile of the Cheshire Cat. In this case, you need the Cheshire Cat. So if direction of time is real, then I would argue that time itself is real. Whether it's emergent from something more fundamental is another matter, but we don't live in a timeless universe in which time is an illusion. Time really is there, and it really has a direction. Now, if time is real, and if time has a direction from past to future, an arrow, then I guess the next question will be, does that arrow have a beginning and does it have an end? Did time start at some point, and will it end at some point? So let's address the idea of time having a beginning. Well, according to general relativity, time began at the Big Bang. That was the earliest moment. And very often people will say, well, how do you know there maybe have been a time before that? Well, in basic general relativity, the answer is that, what do you mean by before? There has to have been a time before the Big Bang to embed the word before in. It's a bit like I tell you to walk to the South Pole, and when you get to the South Pole, keep heading south. It's meaningless. Once you're at the South Pole, every step you take will take you back north again. That's the furthest south you can go. There is no point on the surface of the Earth further south than the South Pole. There's no point in time earlier than the first moment when time was created, along with space and matter and energy at the Big Bang. In fact, people like Stephen Hawking have even come up with ideas that suggest that there's a smoothness to space and time, that as you get closer and closer to the Big Bang, time loses its meaning. It becomes like another dimension of space. And so, in that sense, time does have a beginning. It's the moment of the Big Bang. Of course, that would be really boring if people hadn't come up with other suggestions, which of course they have, speculative ideas. For example, the notion that the Big Bang was simply the moment of birth of our universe. What if our universe is simply a bubble within a much larger multiverse, which is constantly undergoing what's called eternal inflation, expanding, and every now and again bubbles appear in this, what's called the inflaton field. Our universe is one bubble. Our Big Bang was the first moment of our universe, but time existed before it. There's some sort of time of the multiverse that is distinct from the time that we experience in our universe. So that's a possibility, that time really does stretch back to infinity. There are other notions that suggest that maybe the Big Bang was the beginning of our universe, but there's a mirror universe heading in the opposite direction. So time for us moves forward, and there's a reflection of our universe moving in the opposite direction. If there's any intelligent life in that universe, they would regard their time as moving forward, and our universe's time is moving backwards, even though we could never ever have access to each other's universes. Then there are notions like time being cyclic, that the Big Bang will evolve forward in time, and the universe will recollapse again in a big crunch, which would form another generation, another universe. And again, this suggests that time, the universe has been constantly being created and destroyed again and again for all eternity. So again, the Big Bang may not have been the first moment in time. Of course, one should also say that once you bring quantum mechanics into the picture, then that notion of a distinct moment, the beginning of time, what's called a singularity of space-time, that gets fuzzy. Quantum mechanics brings in fuzziness, it brings in uncertainty, suggesting just like relativity brings in a fuzziness in what we call now, because of the relativity of simultaneity, quantum mechanics brings in a fuzziness to that earliest moment of the creation of space and time. These are theoretical speculations. One may even argue as to whether they are real scientific theories, because we don't yet know how we might test them. What observations can we make that would give us evidence that those theories are correct. Maybe sometime in the future we'll be able to tell that. But for the moment, most physicists, cosmologists would argue that the Big Bang was the beginning of time and leave it at that. Of course, the other question then is, does time have an end? Does that arrow continue into infinity, or does time come to an end? And again, there are various options. So one option indeed is that one day the universe will reach a point of maximum expansion and then recollapse in on itself into a big crunch, and that would be then the end of time. Maybe that big crunch then becomes a Big Bang for a next generation universe in which time becomes cyclic. But what we think now is that the universe will continue to expand forever, ending in what's called the heat death. And this will be billions, trillions of years into the future. But it would suggest that time would carry on forever. Now, the reason for that is because just over a quarter of a century ago, astronomers discovered that what we thought should be happening, which is that space is slowing down in its expansion because gravity of all the matter and energy in the universe should be putting the brakes on. No one anticipated that it would start expanding at an ever faster rate. Now, that was what was discovered in 1998 when astronomers looked at the rate of expansion by looking at very distant galaxies and working backwards to figure out that actually the universe is getting bigger now at a faster rate than it was in the past. This suggests that it will never recollapse in on itself. It will just carry on expanding forever. And we're left with this, one might argue, bleak scenario, although I never know why. Why is it a bleaker scenario for the heat death of the universe? Why is that bleaker than the Big Crunch, which is quite catastrophic in my view? But the heat death of the universe will be the ultimate fate of our universe. When all the stars stop shining, they convert all their nuclear fuel, use it all up, and they die. Some will collapse into black holes. Matter will gradually get colder. Black holes will evaporate, according to Stephen Hawking, what's called Hawking radiation, just giving out thermal radiation, and the black holes will then shrink and disappear. Ultimately, the universe will just end up emptier and emptier, just full of thermal radiation that's getting colder and colder and colder. Now, of course, this will be a universe in thermal equilibrium, which comes back to this other idea that, well, will time cease to exist at thermal equilibrium? Well, no. If we were able to, or if a Boltzmann brain were to suddenly appear out of the fluctuation of thermal equilibrium, and that Boltzmann brain could think, and just through sheer chance it evolved some way of seeing the universe around it, it will see the rest of the universe in the thermal equilibrium, and it wouldn't be able to discern the directionality to time. But time would still exist. The universe, if it's going to expand forever, will continue to expand, and there will be a directionality to time in the direction of the expansion of the universe, in the direction of the further cooling down of the radiation that's left in the universe. So, in that sense, time would go on forever. It would be a very boring universe. Nothing would happen. But just because nothing is happening doesn't mean there isn't time continuing, because that would be defined by the continuing expansion of space. Now, of course, there is a third scenario, which is that the expansion of space, which we now understand is due to what's called dark energy, the nature of which we're still trying to determine for sure. Dark energy is making the universe expand ever more quickly. It's winning the battle against gravity. So gravity of all the stuff in the universe is trying to slow the stretching of space. Dark energy is making space stretch and expand ever more quickly. We still don't know the details of dark energy, and it may be that this is something with an influence that will grow over time. So the expansion will get ever quicker and become evident at ever smaller scales, ending up with what's called the Big Rip, in which it's not just the space between galaxy clusters, the emptiness of space that's stretching, but even the space within galaxies, within stars, within planets, within atoms, ultimately will start to spread and increase and rip the universe apart. None of this we need worry about. There's no existential threat to us. We should be much more worried about when our sun stops shining, or indeed more worried about looking after our own planet in the near future, not worrying about what's going to happen to the universe trillions of years into the future. But all those options are open. My bet would be then, I guess, and this is not the way physicists should argue, just I have a feeling or opinion, but my view is that the universe did have a beginning, but won't have an end. Keep on going forever. Which, when I think about it, I realize also is probably not that sensible. Maybe if it doesn't have an end, it shouldn't have a beginning either. Maybe time is eternal in both directions. There we go. This is where we shrug and turn to the philosophers to help us out. Okay, so if you've come with me this far, and we've been through some heavy stuff, talking about arrows of time and unifying the laws of physics and so on, maybe it's time for some fun, a little bit of dessert. A question I'm often asked when it comes to the nature of time is whether we can travel through time. After all, if you think about time, according to Einstein, as part of four-dimensional space-time, then I can move through space. I can exist at this point in space or that point in space, and I can come back to this point, and I can travel around. How is it? Why is it that we can't do the same with time? Why can't we move up and down the time axis? Why are we stuck inexorably moving along the time axis when all times supposedly are there and exist? Well, of course, time isn't exactly like another dimension of space. It is different. It is special. Einstein's theories of relativity may not be the last word on whether or not we can travel through time, but they're the best we have at the moment, and they do tell us something about the possibility of time travel. Of course, we've all watched many movies and TV shows involving time travel. I don't want to go on record for, actually criticizing the really bad time travel movies, Hot Tub Time Machine, but there are also some really intelligent ones. But real physics says when we talk about time travel, we have to make a distinction between the possibility of time travel into the future and time travel back into the past. And it turns out one is easier than the other. Time travel into the future is easy. And I don't just mean if I sit still, tomorrow will eventually arrive, I've time traveled into tomorrow. No, what I mean by time travel into the future is getting there before everyone else. And relativity theory says this is possible by slowing time down. So if I were to head off in a rocket at close to the speed of light and zip around the galaxy for, I don't know, a week, when I come back to Earth, by virtue of traveling very fast, but also, one should say, because I'm accelerating and changing direction, and therefore acceleration being equivalent to gravity means my time is running slower. Essentially, less time will have elapsed for me when I return to Earth than has gone by on Earth without me. So I may have only experienced a few weeks of time travel, but I may return back to Earth years in the future. In a sense, it's not real time travel because it's not that the future was already there waiting for me. I've just sort of fast forwarded to the future. I've moved in along a different timeline, a different world line through space-time, and arrived at the future with less time having gone by for me than for everyone else. But as far as I'm concerned, I could arrive in the future arbitrarily in the distant future, depending on how closely I got to the speed of light or how strong a gravitational field I felt. So in the film Interstellar, Matthew McConaughey's character is an astronaut. They land on this water planet that's in orbit around a supermassive black hole. That gravity is slowing time so much. The astronauts in the movie know that for every hour they spend on that planet, 7 years are going by on Earth. And then sure enough, Matthew McConaughey's character has time traveling in the future, having not aged that much. He's not been away that long, but his young daughter's now an old lady. Whether or not you regard that as real time travel is up to you. Much more interesting, of course, is whether we can time travel back into the past. And again, general relativity doesn't rule this out. Theoretically, we can think of such notions, what are called closed time-like curves, which will be the equivalent of riding on a roller coaster and doing a sort of loop-the-loop. As you're traveling along it, your time is unfolding normally, but you would loop back in time. You could arrive back at the point in space that you left, but at an earlier moment in time. So you can travel back in time that way. The problem, of course, is that this leads to all sorts of paradoxes. So while general relativity strictly doesn't rule out time travel into the past, it leads to all sorts of conundrums which we find rather difficult to get over, such as the famous grandfather paradox. You go back into the past and you're not very nice, so you kill your grandfather before he's met your mother, your grandmother. They never meet, they never marry, your mother's never born, therefore you're never born. And if you're never born, who killed your grandfather? It wasn't you, you have the perfect alibi, you didn't exist, so he doesn't get killed. I've always found that rather strange. Why would you skip a generation? Why not just go back and murder your own mother? Not very nice, I know. But it can make it even bleaker. Go back and meet your younger self. And then, and kill your younger self. So if you never grow up to be a time-traveling murderer, then you don't get killed. So you do grow up to be a time-traveling murderer, and so on. So there are many such paradoxes that would suggest that time travel into the past is impossible. However, we don't yet know where the loopholes are in our laws of physics that would rule them out. Typically, what many might say is that the only way out of this is to subscribe to potentially an even more fantastical notion, which is that we live in multiple realities. So there are parallel realities. Certainly there are areas of physics that would suggest this is true. In cosmology, there's the idea of the cosmological multiverse, bubble universes that have their own big bang, that are formed. In the quantum world, one of the popular ways of explaining the weirdness of the quantum world is to subscribe to what's called the many worlds interpretation, that every time anywhere in the universe, down at the quantum level, something's faced with a choice, the universe branches into multiple options. Famously, Schrodinger's cat in the box that's dead and alive at the same time, and you open the box to make up its mind because it's made of atoms, and atoms can exist in multiple states. While in the many worlds interpretation, there's a you that opens the box to find an alive cat, and there's a you that opens the box to find the dead cat. So these parallel universes exist. This helps us if we're trying to insist on the possibility of time travel into the past. The murdering time traveler can go back in time, but in doing so, they inevitably slip into a parallel reality. In that reality, they can meet and indeed murder their younger self. All that happens is that they will never then grow up in that universe, but the murderer was born and was never murdered in their own universe. So you can have multiple realities. And again, many science fiction writers have written about this, but do we have evidence of parallel realities? Well, no more than we have evidence that time travel into the past is possible. One way many commentators have tried to support the notion that time travel into the past is possible and to rule out paradox is the so-called Novikov self-consistency principle. The idea that if you were to travel into the past, then, and you can interact with the past, you can alter things, but you can only make them turn out the way they have turned out. So the example I used many years ago when I was explaining this was the notion that we know 66 million years ago an asteroid hit the Earth and wiped out the dinosaurs, and that allowed mammals to evolve and humans to evolve from them. Had that asteroid not hit the Earth, maybe dinosaurs would still be around today and we wouldn't exist. Well, what if someone in the future invents a time machine and takes some nuclear weapon back in the time machine 66 million years in order to destroy the asteroid so that it doesn't hit the Earth. But when he gets back there, he sees an asteroid actually is much bigger than the one he recalls, and he does his best and fires his nuclear missile at it, fragments it, but a smaller fragment remains that hits the Earth, wipes out the dinosaurs. And so, had he not traveled back in time, something else would have happened. Maybe it would have missed the Earth entirely. So the fact that he traveled back in time caused the past to evolve the way it has into the future. There are problems with this, of course, and people argue it gets rid of paradox. It doesn't, because what if he decides not to go back? What if he gets back to the past and sees that and thinks, "Oh wow, my nuclear missile isn't going to be able to destroy this. I won't even bother." What if you go back? The one example is a time-traveling scientist. He gets up one day and finds a manual for how to build a time machine in his lab. He uses that manual to build a time machine, and finally, when it's built, he gets in the time machine, takes the manual with him, travels back in time, and leaves it in the lab for his younger self to find. All perfectly self-consistent. But the problem is, A, where did that manual come from in the first place? This is information, this is knowledge that seems to have been caught in a time loop, round and round forever. And secondly, what if he decides when he builds the time machine not to go back in time, or not to take the manual? He has to do it because that's how he found it. So there's a real assault on free will here. We are forced to do something because the future determines the past. One way that many scientists have got around the idea of the laws of physics allowing time travel into the past is to simply say that it's forbidden for some reason. Stephen Hawking famously said, if time travel into the past is possible, where are all the time travelers from the future? Surely they should be among us today. Stephen Hawking, had his tongue firmly in cheek when he said this, because he knew the answer. Of course, it may be there are no time travelers today simply because, maybe there are, and they're just keeping a low profile. Maybe there aren't because no one wants to come back to 2025. They're waiting for us to sort the planet properly and solve the climate crisis and so on before they organize package tours back into the past. Or it simply could be, the most sensible answer is that there are no time travelers from the future among us today because we haven't built a time machine yet. If you build a time machine, the earliest moment you can use it to travel back to is the moment you turned it on, because that's the moment you hook up that moment in time, and then into the future, you can, at any moment in the future, you can go back to that moment. But you can never go back before the moment because there wasn't a time machine that existed back then. Of course, for now, the idea of time travel into the future and the past is makes for great stories and great movies, but much of science and the technology that we've developed from science today would appear like magic to someone 1,000 years ago, or even 100 years ago. So, to what extent might we know so much more about the laws of nature 100 or 1,000 years from now, and look back to 2025 and say, "Wow, weren't we naive in thinking that's not possible, or that's silly?" Maybe in 1,000 years from now, we've figured out how to create a wormhole in space that can be used as a time machine. Who knows? One thing is for sure, we should never be so arrogant in thinking that we already have all the answers. We know a lot about the universe, and a lot of what we know we don't think is going to be overthrown for very good reasons. But we don't know everything. So who knows what we might discover in the distant future.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.